Good morning, students. Today's topic is Nyquist criteria. Nyquist criteria. The Nyquist criteria is used to identify the presence of roots of a characteristic equation of a control system. In a specified region in S plane. From the stability point of view, the specified region being the entire right hand plane beyond the imaginary axis of complex S plane. So what is Nyquist criteria? Nyquist criteria is used to identify the presence of roots of a characteristic equation of a control system in a specified region in S plane. In S plane. So if I find or if I make a specified region in this S plane, if I find a specified region, then Nyquist criteria, by using Nyquist criteria, we can identify the number of roots in this specified region. Right? And what is the stability criteria in S plane? In S plane, the stability criteria say that if the poles are in the right half of the S plane, or if a single pole is in the right half of the S plane, the system will be unstable. The system will be unstable. Right? And if the all poles are in the left half of the S plane, then only the system will be stable. If any one pole lie on this imaginary axis, then the system will be marginally stable, system will be on the verge of stability. System will be on the verge of stability. Right? So, what Nyquist decided? Nyquist decided to select the specified region, as the entire right half plane, and since this criteria is used to identify the presence of roots of the characteristic equation. And what is the roots of characteristic equation? The roots of characteristic equation is the poles of the system, poles of the transfer function. Right? Roots of the characteristic equation means poles of the transfer function, which determines the stability of the system. Right? So, if Nyquist criteria is used to identify the presence of these roots of the characteristic equation in this specified region, then why not we select the specified region as entire right half plane? If any one root in this region, in this specified region occurs, then Nyquist criteria will identify that root. Right? If any one root will lie in this specified region, then Nyquist criteria will identify that root. And if Nyquist criteria says that there is a root in this specified region, it means the system is unstable. Otherwise, either the system is stable or it is marginal stable. Either the system is stable or it is marginal stable. Right? So, from the stability point of view, the specified region being the entire right hand plane beyond this imaginary axis, of the complex S plane, right? Of the complex S plane. How Nyquist criteria differs from the Routh-Hurwitz criteria? How Nyquist criteria differs from the Routh-Hurwitz criteria? The Nyquist criteria differs from RH criteria as first, the open loop transfer function Gshs is considered in Nyquist criteria instead of characteristic equation 1 plus Gs Hs is equal to 0. So the complexity reduces. How Nyquist criteria differs from RH criteria? In RH criteria, we use this equation, characteristic equation 1 plus GSHS is equal to 0, which enhances the complexity in computation. But in Nyquist criteria, we use this open loop transfer function, just GSHS, right? Only GSHS is considered in Nyquist criteria instead of this characteristic equation, right? And second thing, inspection of graphical plot of GSHS enables to get more than yes or no of RH criteria regarding stability of control system. Stability of system. Since observation from graphical plot is much more easier than any computation. By observing only graphical plot, we can say that the system is stable or not in case of Nyquist criteria. But in case of RH criteria, we have to compute or we have to concentrate on the computation to identify the system is stable or not. Right? So these are the 2 points where Nyquist criteria differs from RH criteria, Rauthervis criteria. This point also says that the Nyquist criteria gives absolute stability as well as relative stability. Nyquist criteria gives absolute stability as well as relative stability, whereas this RH criteria gives absolute stability and in some conditions it gives the relative stability. In some conditions it gives the relative stability. But Nyquist criteria gives absolute stability as well as relative stability. Now mapping from S plane to GSHS plane. mapping from S plane to GSHS plane. S being considered as independent complex variable and the corresponding value of GSHS is being the dependent variable plotted in another complex plane called GSHS plane. Thus, for every point in S plane, there exists a corresponding point in GSHS plane. For example, let GSHS is equal to S plus 1.5 and S being transversed in S plane along a line through points SA 1 plus J1 SB and SB minus 2 or plus 2.8 plus J 0.5. The value of GSA HSA will be 2.5 plus J1 and that of GSB HSB will be equal to 4.3 plus J 0.5. If S is the independent variable and Gshs is the dependent variable, if S is the independent variable and Gshs be the dependent variable, then another complex plane which plots this Gshs by using this independent variable S, we name the plot as Gshs plane. We name the plane as Gshs plane, right? And therefore the value of Gshs will be valid for every S. Means if in S plane there is a point sigma plus j omega, then there will be a corresponding point in Gshs plane, because S is the independent variable and Gshs is the dependent variable, right? So Gshs plane is nothing but it is the dependent plane of S plane. It is the dependent plane of S plane, right? For example, if I take it graphically, then this is S plane and this one is Gshs plane. Here we have SA, one J1. Here we have SB, and if S is traversing from SA to SB, and if I join these vectors, from this origin, or not from the origin, since it is S plus 1.5, then this will be 0 when S is equal to minus 1.5 here. In the S plane, it becomes 0 when S is minus 1.5, like this. Then the value of GSA will be 2.5 plus J1, 2.5 plus J1, and this one is 4.3 plus J 0.5 here, GSB HSB. So here also the point GSA HSA will traverse from this point to GSB, HSB. And now the origin will be where? At 0. It means what we did nothing, just replace this 0 to this 0 in GSHS plane. We just replaced this 0 with this 0 in GSHS plane. It means where we are encircling this point, where we are considering this point in S plane, we are focusing origin in GSHS plane. We are focusing origin in GSHS plane. Right? So, what is the conclusion? In the S plane, the 0 of the transfer function is at S is equal to minus 1.5. Thus, a phasor diagram from this 0 to SA and SB is shown. The magnitude and phase of these phasors give the value of GSHS at SA and SB are shown in the GSHS plane. Here, this is a phasor from this 0 of transfer function, right? And the magnitude and phase of these values SA and SB give us the values of GSA, HSA and GSB, HSB in GSHS plane, right? In the next video, we'll discuss this topic, discuss Nyquist criteria, Nyquist stability criteria in more details. Thank you.